This video covers the PID experiment over liquid level control.
The PID parameters that we will consider for this lab are Kc, the controller gain, tau I, the integral time constant, and tau d, the derivative time constant. From gaining experience tuning a PID controller through in-lab experiments, the system dynamics can be determined. In addition, initial PID values are to be selected using the following tuning algorithms: IMC, ITAE, and Ziegler and Nichols. Then, initial PID values are to be tested to determine how effectively these initial parameters control liquid level in the system. From this, the optimal PID parameters can be found for the 8-inch diameter tank. Finally, experimental results are compared to model predictions. Optimal PID parameters are modeled in Simulink, and a sensitivity analysis can be performed.
So the first part of the theoretical background to cover is the Ziegler and Nichols step response method. In this method, we manually created a step response curve in order to find parameters that define the controller. So the controller is first manually set to an initial value and allowed to achieve steady state at that value. After it's reached steady state, the time is zeroed and the controller is again manually changed by a unit step. So with that unit step, it's again allowed to reach steady state. And with that step input, we get a step response curve. That step response curve can be analyzed to determine variables from the first order plus time delay model, which was the model that we assumed for our controller. So we got dead time, theta, lag time, tau, and process gain, kp. And these variables were then used with the tuning methods. So the first tuning method that we used was the internal model control, or IMC. This method is based on an assumed process model like the one shown. And then the controller can be designed using the two steps laid out here, or one can refer to table 12.1 from the textbook. As you can see from that table, we used cases G and H. G was being used to determine the PI parameters, so a PI controller, or proportional and integral parameters. So we got controller gain, Kc, and integral time, tau I, from case G. And then we used case H to determine a PID control, so proportional, integral, and derivative control, so Kc, tau I, and tau D. The second tuning method that we used was ITAE, or integral of the time-weighted absolute error, which you can see the base equation for here. And then that was used with a table from the textbook as well, table 12.3. We used all four different cases, so disturbance PI and PID, and then set point PI and PID. And those use design relations as shown at the bottom of the table.
Considering the general material balance of accumulation equals N minus out led to the development of the material balance used for this laboratory experiment shown in equation 2. Equation 2 was developed by assuming incompressible flow and constant temperature for our system. Further, the volumetric flow rate out was obtained from pressure drop, and equations 3 and 4 were utilized in order to develop an expression for the change in height with respect to the change in time shown at the bottom of the slide. In this expression, the second term is a nonlinear term in which we must linearize. The linearization is shown in equation 5. It's important to know disturbance variables for our system are defined in equations 6 and 7, as well as the steady-state values are denoted below. In order to develop a transfer function for the system, equation 5 is subtracted from the steady state. In order to develop a transfer function for our system, the Laplace transform was performed. The standard form for a height disturbance with respect to the inlet volumetric flow rate disturbance is boxed on the slide, and the gain and time constant are defined below. Further, we can develop a relationship between the output disturbance and height disturbance by assuming the relationship between the valve opening and flow rate is linear. We can plug equation 9 into the previous slide standard form expression in order to develop the standard form expression on this slide, relating the height disturbance with the output disturbance, where kV is the valve gain. The transfer function is then defined below.
For safety, there are a number of hazards one might consider listed in this slide, and the ones of particular importance are in bold. So the first thing to take note of is pressure. The system is open to the atmosphere, however, the bottom of the columns can have high pressure due to the amount of water present, so up to 30 psi. One should always wear protective eyeglasses and monitor the pressure gauge. There's also a lot of water present in this experiment, so just making sure to keep the area dry around electrical outlets or sources of electricity, and just using caution around outlets in general is important. Again, one should always make sure to clean up any water spilled on the ground to prevent any slipping, and use caution when climbing up and down the ladder. For ergonomics, use caution when climbing the ladder again, and understand just how sitting for long periods can affect the body. And then for personal safety, one should always wear lab goggles while in the lab and wear a hard hat to use the ladder. In addition, while there are no hazardous chemicals involved with this experiment, other experiments running concurrently might make use of hazardous chemicals, so it's always a good idea to wear a lab coat while in the lab.
Shown here is an example of a PID that can be drawn for this system. In this experiment, we only use tank 1. So, the water is pumped up from the reservoir all the way up to the top of tank 1, and it goes down, and then it can either come out of the drain exit valve or the exit into the top of the blue tank, where it would then go out of the blue exit valve and go down. Also shown is the controller in the middle. That's the actual PID controller that we are tuning for this experiment. Other things that you can see on this PID are all of the valves involved, the sight glasses on each of the tanks to see the liquid level, and the pressure transducers. Before running the experiment, a calibration should be performed to make sure the equipment is recording correctly. This is done by filling a desired tank to the top and lowering the liquid level incrementally after opening the drain valve. This should show a linear relationship between the tank height and the voltage. The next part of the procedure is to obtain the tuning parameters using the step response graph and the Ziegler-Nichols method. Next, we'll show the procedure for operating under PID control.
Music make you lose control. Music make you lose control. Music make you lose control.
The next couple slides are the results from this experiment. First, I'm going to show you the Ziegler-Nichols step response results. To use the Ziegler-Nichols method, the normalized liquid height was plotted as a function of time after a manual change to the controller input was made. This can be seen in the figure here. For the first step in this method, a tangent line was drawn at the point with the steepest slope and a horizontal line was drawn at the time it takes to reach 63% steady state. The intersection of the tangent line with the initial steady state, or normalized height of 0, gives the dead time. The intersection of the tangent line and the 63% steady state line gives the time constant tau plus theta p on the x-axis. To find tau p, subtract theta p. Theta equals 8.9 seconds, which is about 0.149 minutes, and tau p equals 189 seconds, which is about 3.29 minutes. The process gain was calculated using the difference between each steady state level divided by the change in percent valve opening. All of the process parameters found for this system can be found in this table shown here.
For examining the effects of PI and PID controllers, the effectiveness of proportional control alone was explored through a sensitivity analysis using controller gains within the range of 3 to 24 valve percent opening per inch. To negate the integral and derivative terms, the integral constant was set to a very large number, such as 10 to the magnitude of 5, while the derivative constant was set to 0. The graph shown is a plot of the step response where the normalized liquid height is on the y-axis and the time in minutes is on the x-axis. The results were as expected in that the increase in the controller gain caused an overall decrease in the offset between the final steady state value and the set point. One result which did not follow the expected trend was the result for the highest gain of 24 valve percent opening per inch. For this run, the offset or deviation from the desired steady state was larger than the previous runs. Overall, it was concluded from this study that proportional control alone is not effective in reaching a new steady state close to the desired set point, because some level of offset will always be present. In order to simulate the effects of proportional control, the values for the valve gain, process gain, and process time constant must be determined based on the equations from the derivation shown previously. From these equations, the process gain was determined to be 9.52 times 10 to the negative fifth power in inches per inches cubed per minute. The valve gain was found to be 20,097 inches cubed per minute per percent valve opening,
When multiplied together, these two values give an overall gain of 1.92 inches per percent valve opening, which is not far from the 2.2 inches per percent valve opening determined previously in the Ziegler step response. The process time constant, tau p, was found to be 3.29 minutes. These parameters were entered into a block diagram in Simulink and used to simulate the effects of proportional control. The inputs into Simulink are shown in the block diagrams below. For each diagram, the process parameters were entered in the form of a transfer function, and the proportional gain control was inputted into the PID controller box. These figures show the results from both the experimental and simulation studies on the proportional control of the liquid level system. It is clear from these figures that the simulation study pictured on the right has no overshoot when controlling the system. This is very different from what is seen in the experimental case pictured on the left, which shows approximately a 20% and a 50% overshoot for the controller gain values of 12 and 24% valve opening per inch, respectively. The results also differ in that the controller gain of 24% valve opening per inch has a much smaller offset in the simulated response to go along with what was expected originally. Make controller parameters from the values for Kp, tau p, and theta p that were determined using the Ziegler response method. For each method, the parameters were defined for both a PI and a PID controller. The controller parameters for Ziegler-Nichols, IMC, ITAE setpoint, and ITAE disturbance were calculated. Each set of parameters was used to observe the response curve when a step change was made to the liquid level setpoint. From the response curves of the four tuning methods, it is clear that the method of Ziegler-Nichols for designing a PI and PID controller can easily be ruled out as a practical option. Both of these controllers show a much larger overshoot than any of the other methods and oscillates around the set point to extend the settling time. The IMC and both ITAE methods are very comparable in this study. Therefore, further evaluation was necessary to determine which approximation would be best suited for this liquid level control system. Slide 13, IMC and Ziegler-Nichols. Upon closer evaluation, the Ziegler-Nichols overshoot for PI controller was found to be 34% plus or minus 9%, and for a PID controller, 55% plus or minus 10%. This result is nearly 10 times as large as the overshoot found for the IMC method, which was found to be 5% plus or minus 8% for a PI controller and 3% plus or minus 7% for a PID controller. Similar to the overshoot found in the IMC method, the ITAE setpoint method yielded a 5% plus or minus 8% overshoot for a PI controller and a 2% plus or minus 7% overshoot for a PID controller. And when using an ITAE disturbance controller, the overshoot was found to be 3 plus or minus 7% for a PI controller and 16 plus or minus 8% for a PID controller. When taking into account the error in the measurement of the liquid level height, there is virtually no error for the three methods of IMC, ITAE, setpoint, and disturbance. Once again, the controller parameters were plugged into Simulink in an attempt to replicate the results found in the lab experiment. Shown are the block diagrams for each control system which was plugged into Simulink. The simulation results are plotted on the right, while the experimental results are shown on the left. Not surprisingly, the simulation underestimated the overshoot for all 4 cases compared to the laboratory results. However, after taking into account uncertainty, the simulated results are not far from what was observed in the lab. An additional study was performed to test the effects of a disturbance by opening a drain valve at the bottom of a tank to simulate a leak. Each of the tuning methods that were not ruled out in the previous experiment were used to return the level to an initial steady state after a dramatic decrease in the liquid level. This was done by turning the drain valve 45 degrees from the vertical and allowing to stay there while the tank returned to equilibrium. Based on the figures shown, the controllers least equipped to handle the disturbance were both ITAE PI controllers. This is because they have a significantly higher overall deviation from the desired liquid level. The best response for the disturbance was the ITAE disturbance PID because it had the lowest deviation and a relatively low offset from the steady state. When considering both studies, the advantages of the ITAE disturbance method are negated by a higher overshoot during the set point change. Therefore, the IMC PI was determined to be the most practical method when applied to both a disturbance and set point change, which could be realistically encountered by this system.
The goal of this experiment was to effectively tune a PID controller to maintain a desired liquid level. This was done by using the Ziegler-Nichols method to obtain gain, time constant, and dead time. These were then used in the IMC, ITAE, and Ziegler-Nichols methods to get the controller parameters. The IMC method was the best because of the response to the disturbance and set point changes. In this experiment, PI control is necessary for the system because the derivative term offers insight into the improvement to the overall control.